Hello everyone. So now we will see the editorial for the problem ये हो गया तो pawri करेंगे from Convex 2.4. So the problem is as follows. You are given two integers n and k, and so what you have to find is the number of decimal numbers or which is of n digits such that there are k number of nines in it. And here by 9 we don't mean just by the digit 9. So in this number that we are going to find, 9 can be present even in the binary form, that is 1001. So let us see an example to understand this question better. So let us say you have this number 1001, 001, 295, 1001, okay. So here 9 is present. The most obvious ones are this and this. So 9 is present already two times here, but the number of 9s is not equal to 2 in this case. Here 1001 you can see is present here, and also here, and also here. Hence in this case there are in total 5 nines present. I hope you understood the question here. So let us see another example here. So you have this number 010019. So here we have the first occurrence of 9 as this 1001, and then we have the second 9 as this. So here there are two nines, and the reason for putting this test case is this is a 6-digit number, so we are allowed to have zeros preceding, say zeros at the start of that number. Hence this is a 6-digit number, a valid 6-digit number. So what we have to do is, for given n and k, we need to find all the total number of n-digit numbers such that it has k nines in it. And by 9 we mean the original digit 9 as well as the binary representation of 9. So one obvious direction to solve this problem, as many would think, is by permutations and combinations. So we can calculate the total number of such numbers by finding the total number of arrangements, so the total permutations and combinations of the occurrences of 9 and also the occurrences of 1001. But the main problem in this approach is that we can have occurrences which are intersecting. For example, there are two lines over here. So counting the total number of such numbers while keeping in mind these kind of occurrences would become too much of a hassle. So there would be too many cases, and hence it will become a really hard problem to do to calculate. So if one wants to try it this way, they can try it, but it's actually too difficult. So now we will see a very elegant approach using dynamic programming. So let us dive into the solution. So the dynamic programming algorithm that we will be using for this question is a special kind of a, DP. So it's called a state DP. So we will see in a short time what do we mean by this state DP. So in our DP, so essentially we will be first giving the definition. What kind of a DP we are going to use, and what is the states that I've been talking about that we will see, and also the transitions. So basically the update of the DP as well as the initializations. So essentially in our solution we will be computing the values of DP IJS, which denotes the number of decimal numbers with I number of digits and j number of nines present in it. Okay, so DP IJS is going to essentially calculate this value. I'll repeat: the number of decimal numbers of I digits with j number of nines in it. Okay, and this S denotes the kind of a state we are currently present. So now let us see what do we mean by the state. So in computer science, there is this very famous notion of a finite state automata, or FSM. If if people know about this, then it would be easy. If not, too, we will see. We will understand it in some time now. So let us say, so in a n-digit number or some number, we want to detect a 1001. So when is a 1001 going to happen? So let us say initially, so we have these circles over here which denote the states in which we can be present in. So initially, so this arrow indicates that we are initially present in this state. Okay. So so initially we are there in this state. Let us say we encountered the number. So the first digit of the number was 1. So that means, so in that case, as you can see this arrow over here, so it says that on encountering a 1, we move from this state R to state 0, right? So now our current state is 0 after seeing 1. Next, let us say we saw a 0. In that case, we can see the arrow that is going out of the state, and on seeing 0, it moves to the state 1. Hence, now our current state becomes 1. So that means that so far I have detected a 1 0. So this is basically saying from here I detected a 1 and then I detected a 0. Now next, let us say we get another 0. Where luckily we get another 0. In that case, we move from this state to state number 2 on seeing a 0. So now we have seen a 1 0 and 0. And finally, if we are lucky, we will see another 1 and we essentially got this binary representation that we were looking for. So in that case, from state 2, on seeing a 1, we go to state 3 and we go into this yellow color state that we can see here. So whenever we get into this yellow state over here, that means that we have essentially seen a 1001. Fine. So now what will happen after this? So let us say we saw another 0 after this. In that case, as we can see here, this arrow goes over here. So so why are we going directly to state 1? So if you can see, if after a 1 if we get a 0, that means we already started a new sequence over here. That is 1 0. So we need to directly go to the second state. So in this case, that's why when we saw 0, we directly move to 1. Next, and if you are lucky enough and if we see a 0 1 again, then we will from state 1 go to 2 and then to 3 and detect another 1 0 0. So if that was not the case, let us say after detecting this one, we were at state 3, we got a 1. In that case, we can see this arrow. So this arrow takes us straight back to state 0. So now we are back to the first condition, that is in a 1001 we are at the first one. So because we have to start from here now. And now if we have a 001, we'll again come back to state 3. So the same thing repeats. Okay, so basically based on which state we are currently present, we know that if we have detected a 1001 or not. So I hope this is clear. So now why do we need to see 1001s only always? So let us say we were at 1 and then we saw 2. So this state diagram here is incomplete. So at 0, if you can see, there is just two outgoing arrows. One is this 1 and the 0. So if we see anything other than 0 or 1, we can straight go back to R, state R, on seeing anything between 2 to 8 or 2 to 9. Okay. So let us just ignore the 9 for now. So on seeing any other digit, we can straightly go back to state R because we are nowhere now. In detecting this pattern 1001, we have reached a state where we did not start detecting it still. So we can go back to the state R and again repeat the same process. So maybe it is possible that we have something like this. So we were at 1 0 and then suddenly we saw a 2. So if that was the case, then again from here you can see just we have the 0 and 1 case. So if you see anything other than that, you can go directly to R. And similarly from this place, that is after seeing a 100, I may have seen something. So basically I did not detect the pattern, but I have to know which state I'm in. So if I see something else, I will go over here. And similarly from here to I can go to state R. After seeing a 1001, maybe I saw some number like between 2 to 8, right? So I hope this state diagram, this is basically called a finite state automata. So you have a set of states and you have a set of transitions, and based on what input you see, you will make the transition from your current state. Fine. So this finite state automata is a little bit incomplete. So I didn't draw the arrows basically for clarity. So, but now let us construct something called a very useful thing called the state table. So, what does the state table tell us? So, if I am at state 0, so what are the different possible ways for me to reach state 0? So, my state 0 says that I detected a 1. So, in what scenarios can I come to state 0? So on seeing a 1, I could have gone to state 0 or I could have gone to state 3. But that is not always possible. Like if I was at state 1 over here, then on seeing a 1, if I'm at this state, on seeing a 1, I cannot go to state 3 because there is no edge going in that direction. But I can go to state 0 from here. That means I can reach state 0 from state 1. So let us write that down. So I can reach state 0 from state 1. Similarly, I from state 2, so can I reach state 1? So this is a little bit tricky because if I'm at state 2, that means I have seen a 1 0 0. Now if I see a 1, so based on the state diagram, I move to state 3 and not 1. So I can never reach state 1 directly from state 0 directly from state 2. So hence we cannot write state 2 over here. But if I was at state 3 and if I see a 1, then I can actually go back to state 0. So that means I can reach state 0 from state 3. So let me write that down. So I can reach it from state 3. Next, and as the most obvious one is this, from state R, I can if I see a 1, I have to go to this state 0. So let us write that down, state R. And we are missing one more thing. So on seeing a 1, if I see another 1, that means I have to remain in the same state. So if I was at state 0 over here and if I see a 1, I have to go back to state 0 because it's again the starting of the pattern. So in this case, you see the self loop over here. This basically detects that. So I can go to state 0 from state 0 itself. So that completes all the possible ways of getting into state 0. Okay, so we have missed one more thing over here. The other cases. So now in our question we have to detect the pattern 1001 as well as the pattern 9, just 9. So in that case we have to define another state. Let us call it state number 4. So this basically we go to the state whenever we see a 9. So in that case we can go to 9 basically state 4 from any state. It is possible to see a 9 anytime, right? So this is basically the extra state that we add. So just keeping that in mind, that means I can from state 9 after seeing a 9 I can see a 1, so I can go to state 0 from here. So from state 4 I can go to state 0. So these are all the states from which I can go to state 0. In a similar way, let us do state 1. That means I'm at 0. I can reach state 1 from state 0. And can I reach state 1 from any other place? Yes, from state 3. That is when I saw 1001 and then I see a 0 immediately. So there are basically exactly two states to go to state 1, which are state 0 and state 3. Next is state 2, this state. So which are the possible states from which I can go to state 2? So I can go to state 2 from state 1. And is there anything else? No, actually. On seeing anything else from any other state, if I see a 0 from any other state, I will have to go to either this state or this state. So we will see why we go to this state on seeing a 0 later. But if I see a 0 after a 1, let us say we have to go to state 1, but we can never go to state 2 directly because we need to see two consecutive zeros to reach state 2. Hence, there is only one possible state, that is state 1 to reach state 2. Next, finally, we are at state 3, our yellow state, and we can reach this state only from state 2 again. That is, after seeing exactly a 1 0 0 and then seeing a 1, I can reach state 3, and I cannot reach state 3 from anywhere else. Hence, this is the only state from which I can reach state 3. And state 4 I can reach from anywhere. So essentially I write down all the states, state 0, state 1, because anytime during when I'm seeing this number, this decimal number, if I see a 9 from anywhere, I will always go to the state 4, and I can see a 9 anytime. It can happen anytime. So I have all the states. Even after seeing a 9, I can see another 9. So even there is state 4 here, and there is state R. So we have all the states listed. And when can I enter state 5? So this is a little bit tricky. So I can enter state 5, the state R, from any state, but on seeing which all input. So this is a little bit tricky over here, because I can actually reach state 5 in two types of ways. One is on seeing any number between 2 to 8, and sometimes even any number between 2 to 8 as well as 0. So I can go to state R even on seeing a 0. And why is that? So let us say we had some kind of a input, uh, 2, 3, something like that, and then I saw 0. So here this is a 0, but it's not part of any pattern yet, because I did not see a 1 before it, immediately before it. So that means, so this 3 over here says that I was at state R. So I can go to the 0, but this 0 has to represent still state R itself, because I did not see a 1. Hence, there is a transition from this whatever previous state to state R even on seeing 0. And when can this happen? So this can happen after seeing a 9. After seeing a 9, if I get a 0, then I will go back to state R. And after seeing any other number between 2 to 8 also, so that means from state R to state R, I will have this transition. So after state 1, state 0, does this happen? No, because on seeing a 0 after state 0, I go to state 1. So hence this transition doesn't happen. And similarly, in state 1, if I see a 0, I go to state 2. So hence this transition also doesn't happen. But after seeing two zeros in my pattern, so if I had the input 1 0 0, if I see another 0, this breaks my pattern. So now I have to start my pattern all over again, but I do not have a 1 to start it. So in that case, I have to go to state R over here for this third 0. So I can go from state 2. And similarly, now after state 3, that means I saw 1. If I see a 0, I go to state 1 and not state R, because my new pattern started on seeing that 0. So the possible states, uh, whenever I can go to state R on seeing a 0, are essentially state 2, state 4 and state R. So hence, whenever I see state 2, state 4 and state R, I can go in 9 different ways. That is any number between 2 to 8 and 0 with 8 different ways. I can go to state R from these three states. And in the other cases, that is state 1, state 0 and state 3, only on seeing 7 different number of numbers between 2 to 8, I will go to state R. So on seeing a 0 from these state, I do not go to state R. So this is basically my state table. So now this state table will help me to build my DP. So now based on this definition of DP, DPIJS, so based on this definition and based on the states that I have, so my final answer that I need is essentially for all possible states s equal to 0 to 5, what is the summation of DP of NKS? So here it means n digit numbers with k nines, and I'm in S state. So I initially at the starting I could be at any state. So hence I take the summation of all these cases, all these states. So now let us see the transitions. So now the transitions are very simple to define after constructing the state table. So the transition goes like this. So let us say I want to compute dpij0. That is I'm at state s equal to 0. That means I'm essentially going to put a 1 at the ith digit. So before this, what can come? So essentially now what I have to see is what are the different possible states I can come from to reach state 0, and I basically take the summation of all those cases. So those will give me the total number of numbers which have j number of nines and I digits, and ends me up at this state, that is at state 0 at this ith position. So now that would be uh, everything I minus 1 and all the states which I can come from. So there are 5 different states for state 0, that is state 1, 3, R, 0 and 4. So let me replace this R with 5 just for a common nomenclature. So that means dp I minus 1 j is 0, 1, 3, 4 and 5. It's just the sum of those. Similarly, if I'm at s equal to 1, that means I have I'm going to put a 0 at the ith digit, and I've seen a 1 before that. Definitely there was a 1 before that. If not, this this kind of transition won't happen. So in what kind of states can bring me to this 1 0? So there are two possible states. One is state 0 and the other is state 3. So state 3 means there was a 1001 detected and then a 0 has come. So these are the two cases. And you notice I do not decrease the j because I still need to find that many number of nines in till I minus 1. So we'll see when j changes. Similarly, s equal to 2, that means I have seen something like a 100, then only I would reach s equal to 2. And this kind of a case would happen again in just one state according to the state table, that is state 1. So it's just dp I minus 1 j1. And one more thing is we need to ensure that I is greater than 1. If not, this is not valid because to reach the state 2 you need at least 3 digits, 3 numbers. So hence I should I should definitely be greater than 1. Else the answer is 0. So there are 0 such numbers. And the next case is s equal to 3. That means I have seen a 1001 now. So now what? So if I have seen a 1001, that means I have a 9 with me now. So in that case, dpij3 would so you can see for state 3 I can come just from state 2. So the answer would be dp I minus 1 and j minus 1 because I have seen a 9 now, and now I'm asking the total number of numbers such that with I minus 1 digits and it's ending with 100, right? I hope this is clear. So I reduce the number of nines that I'm going to search for, right? So now I'm going to ask what is the answer till here. Fine. And this also I can check only if j is greater than 0 because I have detected a 9 over here. So there should be j should be at least 1 in that case, and I should be greater than 2. And this comes from the same reason that to reach state 3 I need to see at least 4 digits. That's why I should be greater than 2. Else the answer is 0. And next we have state 4. That means that I've seen a 9. I'm going to put a 9 here. And as you have seen from the state table, you can come to this state from any of the other states. So it's just a summation over all the states, and we also decrease the j values because we have just detected a 9, right? And finally state 5. So now I'm putting a random number. So now as we have seen these two different cases, so this means that I'm allowed to even put a 0, and this means that I'm not allowed to put a 0. For these states I do not allow to put a 0, and these states I'm allowed to put a 0. So hence the value would be exactly that. Fine. I hope these DP transitions are clear. So once we have this, we just need to run the algorithm. So we just have the transitions now. But what are the basic base cases? So the initialization goes like this. So the case when n equal to 1 and k equal to 0, that means I'm searching for one digit numbers with no nines. So I can have the numbers 1, 2, 3 and so on, 0 also. But I cannot have a 9. So there are totally uh, 9 choices. but it also depends on which state I'm in. So if you notice, if you n equal to 1 and k equal to 0, and if I'm at the state 0, that means I have to put a 1 over there. So the answer would be 1 in that case. But if I'm at state 5, I have now 8 different choices from 0 next 2 to 8. So I have 8 choices. So hence this completes my entire line. And let's see the logic of why this happens. Why are all these values 0? So the main logic is that we are at n equal to 1. So you cannot reach state 1 or state 2 or state 3. And as k is equal to 0, you cannot go to state 4. You cannot put a 9. Hence it's 0. And the other base case is when n equal to 1 and k equal to 1. So you're searching for 1 9 with one digit. And that can happen only if you put a 9. So that's why DP of 114 is 1. And everything else is just 0. Fine. So that is basically the base cases. So now you run the algorithm. But these values can go huge. So the question asks to compute the value modulo 10 power 9 plus 7. So hence we use the basic rules of modulo arithmetic. And the final answer would be something like this. So the time complexity is it takes number of test cases, and as we are going over every such digit and for all possible k, and it takes a number of states square in each for each of these cases, because the worst case is when you are computing for this case, so you have to take the sum of number of states. So whenever the number of states are there, that many number of terms you collect, and you take the sum of those, and you do this for every state. So hence it takes number of states square to compute. So essentially the algorithm runs in time order t into n into k into number of states square, and the memory it takes is just number of states. So n into k into number of states. So given the constraints, this is fine. So this algorithm would work, but you can actually optimize in terms of memory. So if you notice for every transition, so for any given I, you always depend on just I minus 1. So there is no use of storing for anything else before I minus 2, right? So you essentially, if you want to compute n, you require just the values of n minus 1. So n minus 1, but all the possible k's and all the states, right? So you just require just one particular uh, k cross number of states matrix. Hence, so basically store the values of just dp I minus 1 js for all j and s. And so the space becomes order k into number of states. So you lose this n dependency on the memory. So that ends this editorial of the problem. So we will be seeing the implementation now. So a bonus question is, can you reduce the number of states? So as we see, there are 6 states here, so it's small enough, but can you reduce it further? So as you will see, the tester solution for this problem uses just 4 states instead of 6, so it's not a huge improvement, but it shows that you can always improve states in these kind of state DP question, and it makes the problem easier. So let us see the implementation. So the implementation is very easy after getting the transitions. You run, so given the input nk, and what you do is, so this is basically optimizing even in the memory, this implementation. So you just store for the previous value a k cross number of states matrix. And so these are the base cases. So this means that n equal to 1 is k equal to 0, k equal to 1. The values are 1 and 8 and just 1 in this case, right? So now you run the loop on n, and you run a loop on k, and just update the values based on whatever transitions we saw, and then update whatever the value of past is to just store the previous one. Fine. And you apply the appropriate modular arithmetic too, and that's it. The implementation becomes very simple once you have the transitions. So thank you.